Okay, so we'll proceed on limit continuity and differentiability as far as 3D is concerned. Okay, so we'll proceed on limit continuity and differentiability. So as far and differentiability as far as 3D is concerned. So what we have discussed till now, that if I have a kind of a XY plane, I have a 3D in a sense that there are two independent components. One is X and one is Y. So two independent component, two independent variables, and they come into picture when there is XY plane. So on the XY plane, we have these two orthogonal components. They vary independently. If they vary independently, then there is a function over it that is fxy, that is z. Now, now at any point a comma b, if I want to check that function fxy is differentiable or not. Differentiable means rate of change per unit change in independent component brings how many unit change in dependent component. In multivariate case, in multivariable case, it is far different than single variable. So in multivariable case, it becomes a surface. When it becomes a surface, then the point at which we are calculating the rate of change means if I am calculating a comma b, rate of change at a comma b, then fa plus delta x b plus delta y minus fab by delta x square plus delta y square root. That is the equation for the calculating the differentiability, rate of change. Rate of change in x direction, rate of change in y direction divided by the distance. But it is not that simple the way it looks because it is two dimensional. The fundamental, if it is single dimension, if it is single dimension, then I know that what is delta x. But if it is in two dimension, then the point at which a comma b, the point at which we are calculating the rate of change, then the delta x and delta y, whatever we are talking about, the next point at which we are calculating is a comma b, the next point, that is a plus delta x and b plus delta y. Now delta x and delta y can vary independently. If that is the case, then all around point a comma b is a point, then we are calculating rate of change when there is another point that is a plus delta x, b plus delta y. Delta x and delta y vary on its own, so full 360-degree it will take. If delta x and delta y are same, then 45-degree it is taking all around. But if one is less, one is high, one is less, then it will take 360-degree. In around along 360-degree in xy plane, we have to calculate the rate of change. Okay, so that is impossible. Means calculating rate of change for each minute angle 360-degree, then for each minute change this is infinite degree. For infinite degree, all around a and a comma b, all around we have to calculate the differentiability. And then if it is happening, then we can say that it is differentiable. Whereas single dimension, only one direction, 0 degree. There we have to calculate. So this is difficult. This is not cakewalk. Calculating the differentiability in 3D is not very straightforward because we have to consider that when we calculate the rate of change in a direction from point A comma B, then direction is omni. So it is 360-degree and it is painful. So now we have to come to some kind of protocol, that what some kind of steps, that what should be done. So in that step, now we have that at point A comma B, the function over two independent variable x comma y should be continuous. Like if I take example of xy by x square plus y square is a function xy by x square plus y square. If that is the case, then limit should exist to prove that it is continuous. So if limit exists, then it is continuous. To get the limit exist, fxy fxy when xy tends to a comma b, fxy tends to fab. That is the scenario for limit to exist. So if I consider this fundamental, then xy by x square plus y square. So for this we need to calculate the continuity if I calculate fxy at a point where it is near to a comma b. So a plus h and b plus k. So h and k are delta x and delta y. So x into y by x square plus y square. So this we have to prove that this is continuous or not. So at point 0, 0. So now it would become h into k by h square plus k square. So if I set h equal to k, then it will become h square by 2h square. So that will become h square by 2h square. So that will become a constant. So if it is a constant, then it is not in control of the, so fxy at point a comma b, some distance delta x and delta y. So if I have a point a comma b, some distance from a comma b, that is h distance and k distance along x axis and y axis, that is should be considered as delta x and delta y. So at other point a plus h, b plus k, the hk, these are the 2 points that are very small distance from a comma b. So if I calculate function f a plus h b plus k, then for the function xy by x square plus y square, it will become a plus h into b plus k divided by a plus h square plus b plus k whole square. So in that case, if a and b are 0, 0 at the origin, then it will become h square plus k by h square plus k square, where h and k are tends to 0. Now, if I want to try to find this limit, then consider that it is from in 45-degree angle, then h and k are same. That is the case, then it tends to h square by 2h square. That is 1 by square root. 1 by square root of the 2. That is a constant. If that is a constant, then fa plus h b plus k, that function is not varying. So if I am at point a comma b, and from a comma b I am at infinitesimally small distance from a comma b, the distance, the next point is h comma k. So the other point coordinate is a plus h, b plus k. Now we calculate the limit of the function f a plus h b plus k when h k tends to 0. So the function is moving, the next point a plus h and b plus k is moving towards a comma b. If it is moving toward a comma b, then f a plus h b plus k should be equal to fab. That is the concept. So if I see the equation what we have taken, fxy equal to xy by x square plus y square, that is 0 when xy is 0, otherwise it is not 0. So when we calculated the limit f a plus h b plus k, that is 1 by square root 2, okay, that should be 0 when, but it is not dependent upon any variable. So it is something like it has some value and suddenly drops to 0. It is not continuous. It makes sense, right? It means if I have a point A dot B, A comma B, and there the value is 0, but just at infinitesimal distance away from this point, all around, there is an amplitude, there is an offset. So it is something like it has some value and suddenly it drops to 0. or it will after that it may take negative or whatever. So it is not continuous at a comma b. If that is the at origin, then it is not continuous. So when we are calculating differentiability at any point a comma b, then the rate of change all around a comma b, when the function, if I have a function fxy, then fxy value at a comma b, whatever is the value. Now if I calculate the value all around and place limit that it will come to a comma b, then there's the rate of change should be continuous in 360 degree. So from all direction, when it is single dimension, then only one direction. It is nice to calculate the differentiability. But for 3D, where xy is a xy plane at any point, then the delta x and delta y, whatever you take, we have to consider all 360. All 360 degree means not 360 point. In one radian change or 1 degree change, there can be infinite angle. So at infinite angle, when it is approaching to a comma b, then it should be the rate of change should be calculatable. So the differentiability calculation in 3D is not very straightforward. So what the steps that protocol we are following, it should be continuous, first of all. That is required. If it is continuous, then after that we see that the partial derivative. So partial derivative means differentiation along x-axis, differentiation along y-axis. They exist at a comma. If all they two exist, it is continuous, and partial derivative also they exist, then we consider, first of all, it should be continuous. If partial derivative exists, then the together, not the only x direction and y direction, because we have to thinking about 360 degree, right? So the both partial derivative together they should exist. So in order to bring it togetherness, then there is a something called tangential surface. At any point a comma b, if I calculate, so if this is a sphere, if this is a solid sphere, that is the 3D, then at any point here, if I want to calculate the tangential surface, the equation of the tangential surface in simple term is mx plus ny, or m1x plus m2y, where m is dz by dx and n is dz by dy. So partial derivative along x-axis into x plus partial derivative along y-axis into y. Same thing in single dimension, y equal to mx, where m is the derivative. If I know the derivative, I know the rate of change, then if I multiply it by x, then that is the equation of the slope that we are getting. If the partial derivative, if the derivative is 0, means there is no slope, that will come as maxima and minima, local maxima, global maxima, local minima, global minima, that we'll see. Local maxima, global maxima, okay, local minima and global minima. So when derivative is 0, means there is no rate of change at that point. So that is the end, that is considered as end point. But anyway, that we'll see. So if I have derivative, then to get the equation of the line, that is slope line, that is y equal to mx. So in 3D, z equal to mx plus ny. So how much the rate of change is along x-axis, so that much distance we keep it, and how much the rate of change along y-axis, that distance we keep it. If we add it, then that much is the actual change that happened along the z direction. So z equal to mx plus ny. It is understandable, right? Means rate of, if I know the rate of change, if I multiply that by independent variable, then we get how much dependent variable change. So if I have a surface, if I have a surface and along the x-axis it is going down, along the y-axis it is coming up, if I have rate of change along x-axis and multiply it by x, then how much down the z gone, that I can calculate. Now rate of change along y-axis if I know, and if I multiply it by y, then how much z value it gained, that I know. If I add these two, then then we can actually calculate the equation of the surface. Okay, this is tangential surface. If this is tangential surface, then if I know the slope along x-axis, slope along y-axis, then slope if I multiply with the x and slope if I multiply with the y, whatever the z value we are getting, that z value if we add, then that is the net z value that we get at any point. Like if I have y equal to mx in the single dimension, if I know the rate of change along the single dimension, so only one thing will come. If I know the rate of change m, then y equal to mx. So with that rate of change, if I multiply x, then how much the kind of offset, how much the displacement we are getting in y direction, that we can calculate. Same way, if I have a tangential surface, not the line, tangential surface if I now know the rate of change along x-axis, if I multiply with the x, if x is big, then there is a big change in z. If x is small, then with the rate of change, the z value is small. So whatever the rate of change we see, then multiply by delta x or x, and whatever rate of change we see multiplied by y or delta y, then that much if we add, then that much that much change we see along the z-axis. So if there is a unit change along x-axis, there is a unit change along y-axis. If I know the rate of change along x-axis, that is partial derivative along x-axis, rate of change along y-axis, that is partial derivative along y-axis, then if I multiply partial derivative along x-axis into x plus partial derivative along y-axis into y, then we get the z value. Okay, so that is the concept. Now, if I know, so still discussion is going on, that if I know that the graph equation is continuous at point A comma B, and the tangential surface which involve dz by dx and dz by dy both partial equations with partial derivative, then how can we assure that it is differentiable? We can be assured it is differentiable when, like the discussion what we did, like if I have I have a 3D, so this is the point we are talking about. This is A comma B. Now at A comma B, this is tangential surface. A comma B, the material, okay, the graph, both are coincide at A comma B. But after that, it takes this shape and tangential surface take this shape. So they are not at the same z value. So z value is different. For the object, the z value grows like this, whereas tangential surface is like. So the difference, the gap between them is keep on increasing. So the gap we address through error. So error at A comma B is 0. Whereas if I go, so if where it is touching the tangential surface, the error is 0 because both are same. But after that, we can see that surface is growing like this for the graph, where a tangential surface go in this direction. So error is nothing but fxy minus lxy, where lxy is the tangential surface equation. So fxy minus lxy is the gap that we are seeing. Like if I consider like this, then the gap is now here at this point there is no gap, but gap is increasing. Can we see? This gap is increasing. So that is error is increasing. So error is nothing but fxy minus lxy at any point. Now, for calculating the differentiability, we see the limit. So at point A comma B, they are same. Then let's take another point, that is A plus h is delta x, and B plus k is delta y. Any point that is A plus h and B plus k. Now, if I have error function at A plus h and B plus k, and where h tends to 0 and k tends to 0, in that case, the error should be 0. Certainly, right? Because error is nothing but difference between fxy and lxy. This difference becomes 0 when xy is a comma b. This is a comma b. At this point, they consider this tangential surface and this graph, the body, the model, they coincide each other, and there is no error there because there is no gap there. But after that, there is a gap. So this gap at any distance h and k from a comma b, if I calculate the gap, if I address that gap as error, then error at a plus h b plus k, when h tends to 0, k tends to 0, then this error also should be 0 because error at a comma b is 0. So the error at a plus h b plus k is nothing but f a plus h b plus k minus l a plus h b plus k. Okay, where h tends to 0, k tends to 0. If that is the scenario, and if this subtraction leads to 0, means error leads to 0 when h is tends to 0 and k tends to 0, because it will come to point a comma b where fxy and lxy surface and graph equation, they are equal. So subtraction is 0, so error is 0. If that is the case, then it should be considered as differentiable because h and k, now we are taking care of all direction. H and k, if okay, if this is the point a comma b and h and k are same, then we are taking, if this is x, this is y, if this is x, this is y, and this is x, and h and k, the value we have taken, if they are same, then 45-degree we are taking, and depending upon the hk ratio, we are taking, considering all 360-degree. So in all 360-degree, if we know that limit exists, then it is differentiable because we are taking care of both partial derivatives. Okay, now let's calculate that. Suppose that I have a function fxy equal to x to the power 1 by 3 and fxy, sorry, fxy equal to x to the power 1 by 3, y to the power 1 by 3. We have already calculated fxy equal to x square plus y square. X square plus y square is this paraboloid, right? This paraboloid. This is a paraboloid. From origin, it grows like x square in x direction, y square in y direction. If I bring it together, then it is a paraboloid. So paraboloid, it is continuous for both partial derivative exist, and then we saw that error limiting h at h tends to 0, k tends to 0 at point a plus h, k plus b plus k is 0. So this is what we have already calculated for the equation fxy equal to x square plus y square. Now fxy equal to x to the power 1 by 3, y to the power 1 by 3. If that is in question, first we will see it is continuous or not. Okay, so x to the power 1 by 3, y to the power 1 by 3 at origin. If that is the case, then if I want to see continuity or not, then h power 1 by 3, k to the power 1 by 3 divided by h to the power 1 by 3, k to the power 1 by 3. So that is the kind of equation that it is showing for the testing of the continuity. So if h and k are same, then h to the power 2 by 3. So that is directly proportional to h. So this is continuous. Now if I see the partial derivative that exists or not, then h to the power 1 by 3, k to the power 1 by 3. If I differentiate along x, I mean x to the power 1 by 3, y to the power 1 by 3, if I differentiate along x and y, then it will be multiple of x and y also. So at point 0, 0, fxy, partial fx, xy, fy, xy, the partial derivative along x-axis and y-axis will be 0, 0, 1. So that exists. Okay, so partial derivative also exists. Now we'll calculate the error a plus h b plus k where h and k tend to 0. If this error is also 0, then it is differentiable. So error is nothing but fx f a plus h b plus k minus l a plus a b plus k. So f a plus h b plus k, where at the origin we are calculating. So h to the power 1 by 3 minus h to the power 1 by 3, k to the power 1 by 3 minus lxy. So for L, FAB is 0 plus MX minus A N Y minus B. So M is 0, N is 0. So that LXY part or LA plus HB plus K part is 0 divided by h square plus k square square. This is the equation that we are considering. So error, so relative error when we see for the differentiability, so error equal to fxy minus lxy. Relative error we calculate for the differentiability. Okay, so fx minus lx by h square plus k square square root. The way we calculate the differentiability. If I want to calculate differentiability in single dimension, then fa plus delta x minus fa by delta x. Like that, for differentiability in 2D, fa plus delta x b plus delta y minus fab by delta x square plus delta y square square root. So in the error also we normalize it with the delta x square plus delta y square square root. So if that is the case, then relative error would be fxy minus lxy divided by h square plus k square square root. So for error a plus h b plus k, error a plus b h b plus k, for the relative error we have next equation as f a plus h b plus k minus l a plus h b plus k divided by h square plus k square square root. Now f a plus h b plus k at origin, a is 0, b is 0, it comes at h to the power 1 by 3. For the equation fxy x to the power 1 by 3, y to the power 1 by 3, it will come at h 1 by 3, k 1 by 3 minus 0, that part is 0, divided by h square plus k square square root. If h and k are same, we are coming from a 45 degree, then h to the power 2 by 3 divided by square root h. Okay, if that is the case, then h to the power 2 by 3 divided by square root h means denominator is higher. So that will come as 1 by square root h to the power 1 by 3. So the relative error equation for the EXY, that is fxy minus lxy at infinitesimal small distance delta x delta y. So fxy minus lxy divided by delta x square plus delta y square. This is for the differentiability. For differentiability, we have to divide by the, because we are calculating per unit. So for the error, relative error we call it. So error E a plus h b plus k, it will come as f a plus h b plus k minus l a plus h b plus k divided by h square plus k square square root. So f a plus h b plus k when a and b are 0, for equation fxy x to the power 1 by 3 x to the power 1 by 3, it will come at h to the power 1 by 3 k to the power 1 by 3, where a and b are 0 0. Minus lxy is 0 because m and n are 0, we calculated, divided by h square plus k square root. If h and k are equal, then the condition happens as that numerator is h to the power 2 by 3, denominator is square root h, then 1 by square root h to the power 1 by 3. So the error is 1 by square root 2 h to the power 1 by 3. H to the power 1 by 3 is in denominator. If that is the case, then it is inversely proportional. If it is inversely proportional, then it is not it is not differentiable. So the function fxy equal to x to the power 1 by 3, y to the power 1 by 3, it is not differentiable. Because the error, or relative error, what we are calculating, it is inversely proportional to the h. 1 by square root 1 by square root into 1 by h to the power 1 by 3, we can say. So when h is tends to 0, error is growing. When h is going away, then error is decreasing. When h is coming near to the origin, error is increasing because it is 1 by. So when it is very near, tends to 0, infinite tends to 0, that is h is 0.00000000001, then error is infinite. So differentiability is infinite. So in that way, we cannot say that it is differentiable. So that is the case we are thinking. So if function is continuous and partial derivative both exist, still we cannot say that it is differentiable. Can we go more simple? what we have seen. So if function is continuous at this point, and partial derivative along x-axis and y-axis exists, then we can go ahead with the differentiability check. When we check the differentiability, then error what we beyond this a comma b, we start seeing the between the error between the model and tangential surface. If that error at point A comma B at a distance infinity with small distance h and k, if we calculate the limiting and that limit becomes equal to FAB, okay, then the error tends to 0. If error tends to 0 and limit exists, that is differentiability. H and k, what we are taking, delta x and delta y, the value of delta x and delta y, we keep changing. In one case, we took h equal to k, delta x equal to delta y. That is 45 degree. Then we calculated it is differentiable or not. It must be differentiable in all 360 degrees. So if this is the point A comma B, and if we come from all 360 degree towards A comma B, where h and k are independent to each other, they're very independent to each other, then all 360 degree are being taken care. If that is the case, then only it is differentiable. Then if, okay, so if all 360 degree around, it is a kind of the error what we are seeing is considered and it is limitable, then error we are calculating through differentiability. Both differential partial derivative along x-axis and y-axis we have taken care, and the final calculation we are dividing it by h square plus k square, means we are checking the continuity of the partial derivative also. If that is the case, then if partial derivative along x-axis and partial derivative along y-axis, if partial derivative, not the surface equation, the partial derivative along x-axis, partial derivative along y-axis, if they are continuous, if partial derivative comes in the form of x and y, like if I have an equation called x square, then if I calculate the differentiation, then it is 2x. It is again is a function over x. If partial derivative are also function over x and y, then if those functions, partial derivative functions, if they are continuous in their direction, then they are continuous in 360 degree. Okay, partial derivative at a comma b, x direction, partial derivative a comma b in y direction. That's why we are calculating error when h and k are delta x and delta y around 360 degree, and we divide by h square plus k square root, because we want the way differentiation happens. But if we go ahead and if you see the partial derivative what we have calculated along x-axis, if it is continuous along x-axis, partial derivative along y-axis, it is full continuous along y-axis, it covers the full surface. If that is true, then it is differentiable. If that is the case, then no need to calculate that the function is continue. It is a kind of it is limitable or it is continued at point A comma B. Okay, so continuity is calculation is not required, because if I know partial derivative is continuing, partial derivative along x-axis and y-axis, if they follow the continuity, then they cover the full surface. If that is the case, then no need to calculate error, no need to calculate continuity, just partial derivative calculate and prove it is continuous in a particular region. If a particular region, if they are continuous, then it is differentiable along the full surface. Okay, so the what we saw, that instead of calculating the continuity at any point and then calculating the error, relative error, that is differentiable error at any point, calculating limit in both directions, then partial derivative at that point along two direction, and then going with tangential and surface equation and calculating. Instead of doing this much, we just calculate the partial derivative along two directions and prove that whatever is coming, both equations are continuous in their own direction, it covers the complete region, and you're in the complete region, the surface is the graph is differentiable. We'll talk more on it. Okay, I mean it is different than single dimension, okay, or 2D and 3D. Can you see the difference? It is more than 10,000 times more complex. Okay, one change 2D to 3D, it is 10 to the power 3 or 10 to the power 4 more time complex. So anyway, we'll continue on this, that how continuous partial derivatives, they contribute to differentiability in the particular region. So that will continue.